Okay, so hope my screen is visible. Now, first of all, apologies for joining late. I didn't realize the session going to happen. So today it's the final session of our series, and today we are going to cover what it takes for a pre-trained LLM, because we started training the LLM using just in a self-supervised manner. So we have a continuous text which is available to us from either websites, books. It's just a continuous piece of text. Now, how to turn that into a conversational based agent or LLM? That's what the post-training or after the pre-training, these post-training stages help the model to learn those nuances of conversation. So let's start with that. Today we are going to cover like two main things. So how do we do instruction following? So let's say if we ask LLM to tell me how to make a tea. So it is taking some instructions from the user, and then on the basis of that, it is giving some set of answers, right? And then how do we ensure that the model output that is generated is aligned to the human preferences? So these are like two things, two subjective things. One is the alignment, and second is human preferences. So we try to objectify or reduce the subjective space by giving them certain rewards for aligning. So aligning is again in quotes because I don't think I'm visible. But the point is that the LLM output should be aligned to those preferences for which the model developer has shown training data. So we'll see like how does both of these things happen. So to start with, um, like pre-trained LLMs, we have seen they are trained on large amount of text of trillions of tokens, and even though they are knowledgeable, they contain the domain knowledge, or probably they know about current affairs. They can do next token prediction. So basically, they are trained on the objective function that they should be able to predict the next token, right? So how they are trained, like we have seen in the last few sessions. What do you mean by like next token prediction? How do we when we start or initialize the parameters of the model during the initial step, then how do we ensure that the model does not go into some other direction? Because they are, again, the parameters that are initialized for the model are again randomly initialized. So these parameters are being learned such that the model is able to predict the next tokens for the given text, right? That's the idea. Now, once the pre-trained model has captured the information that has been shown in the data during the pre-training stage, now comes the post-training stage, which tries to bridge the gap between the just a generic prediction, like generic prediction in the sense the models that we used to see in the deep learning in the like 4 or 5 years back, pre-generative era, is like they are mostly suited for single prediction or single task, or let's say few set of tasks, but they are not for like generic suitable for the generic task or all set of tasks. Now these post training helps it to align, helps it to enable it to give conversational kind of feature to these pre-trained LLMs and make them usable to the end user for multi-purpose applications. So let's start with like how does the output of the pre-trained LLM and the supervised fine-tune, that is, let's say post-trained LLM looks like. Now this is the output of the Llama 3 8B, which I ran on my system. This is only pre-trained checkpoint. There no supervised fine-tuning or alignment happens. So let's say if I ask who is the president of India, so it will just it will just recall from the pre-training data like what is the kind of things that I have to fill in after this text, right? So it's just doing some kind of a next token predictions. So the president of India is the head of the state and first citizen of India. The president of India is the first citizen of India and the head of state. So like you see, it's trying to repeat the first two sentences by doing some permutation, shifting the last part of the first sentence to the first part in the second sentence. The president is the constitutional head of the executive government of India. So here my intent was who is the president of India? It should spell out the name, right? But it is not able to do that because this is just trained for the next token predictions task on the pre-trained without explicitly telling like how do you need to answer for a particular set of queries or set of queries. Now this is GPT OSS 20B. It's post-trained LLM. So this is again a reasoning LLM. So it will also mumble the certain things, that thinking tokens that we call, before answering the giving the final answer. So the user asks, so who is the president of India? So now the thinking tokens have started, like they likely want the current president as of 2025. So it is trying to fetch the information from the from its data, the model parameters. I mean, it's not literally fetching from the model parameters, but it's trying to recall like what the particular query, input query, and the output should be, very close to each other. So the question is, who is the president of India? Should answer Draupadi Murmu, etc., etc. Provide some details, and at later point of time, I think it provided me answer like the president. So answer accordingly final. So yeah, from here the answer starts. Draupadi Murmu is the current president of India. She assumed office on July 25, 2022. Like so, like you probably got the difference between the pre-trained LLM and the post-trained LLM. How does the output differs? And this is particularly stark because this particular LLM produces a lot of thinking tokens while making the final answer. Yeah. So what are the things that are learned during pre-training stage? So the knowledge about the domains, about the data for which the model has been trained upon, has been learned almost entirely during pre-training. What alignment teaches it, so basically you think from the mathematical perspective now, that the objective of learning the model parameters is to learn the input data distribution. So whatever, how my data has been generated, the ground truth data which I'm, or the pre-trained data that I'm feeding to the model. So the model parameters tries to learn the data distribution or how the data has been generated. And once the model has learned that distribution, it can generate any kind of data, which is similar to how the pre-trained data or human would have written, right? So idea is to learn that data distribution. Now, once the data distribution learns the model knowledge, the domain knowledge, the alignment tries to learn like which sub-distribution of format should be used when interacting with users. So, like, the way you can think of like the person from, let's say, Rajasthan or will answer differently about the process of making tea than the person who is from, let's say, Tamil Nadu, right? So maybe in North India, we put a milk a priori while making a tea, and Tamil Nadu, it's slightly different. I'm not trying to generalize, but like that's my observation. So there are different ways of answering a question. So alignment, in the sense, the idea is, the intuition is to tell the model that there are like different distribution of the data from which you need to align, and probably you need to ask the query before answering the final question. So like if you've seen the recent LLMs, the recent updates to the LLMs, basically in the proprietary LLMs like GPT or Claude, you will see like those LLMs now try to ask a question before, if they are confused about if there are different ways of answering the question, right? You might have seen that, because I've seen that very recently, like in the past week. So now the idea is that we should align to the, the idea of post-training is to align with the distribution of different formats, the data, the different formats of answers that could be possible. And how does the scale of data changes? Now we know that in pre-training we use trillions of tokens, but in the post-training stage, we only require like few thousands or few million samples to make the model learn the way of doing a conversation with the user. So that's the idea. Like the data scale changes, probably the objective function in which you train the model changes. So these are like two key differences between them. And I told you about the intuition as well. So yeah, here is the base model, and we have like few thousands, or let's say few millions of instructions, which gives our supervised fine-tune model. So this supervised fine-tune. So what are these human instructions? We'll go into that a bit after 2-3 slides. And then we use human preferences to along with the reward model, which rewards basically how this particular SFT model has generated, let's say, some output A for, let's say, how to make a tea, and the model has generated output B to tell you like how to make a tea. Now, which output is preferred, output A or output B, is being decided by this reward model. And on the basis of this reward model, my supervised fine-tune model is adjusted to give you a better human-aligned model, which is more highly rated by the user. So, um, uh, it's useful for the users, end users. That's the overall idea. There are two set of tasks that we have to do. One is supervised fine-tuning. So here in the supervised fine-tuning, the loss function objective remains same. So it's same, that is the next token prediction. But in alignment stage, so first is the instruction following stage and second is the alignment stage. So in the alignment stage, there are different ways to fine-tune the parameters of the model. So we'll see like what are the different ways, but this is like a broad bird's eye view of how the final model that we interact with arrives in this process. Yeah. So instruction tuning is the foundation of post-training for building useful models that can do conversation with the users across task and domain. So not only conversation, they are able to do tool calling also. So let's say you have seen like recent updates to the LLM, like in last 5-6 months, the model has become more often like agentic features. So what happens is in these newer kind of reasoning models, the model is, if you're given like 5 choices to the models, let's say if you tell us like what is 10 plus 5, or like what is 10 multiplied by 5. So now if you provide set of tools to it, let's say if you do, tell me the computation of what is sine 10, okay, sine function, the value is 10. Now, if you have provided a set of tools that is calculated to the model, so it will eventually call the calculator to do the computation and return back the results. So it don't have to just fixate it with just the knowledge that it has learned. So similarly, it can do web search queries by scraping the web pages in real time to find out the latest information. So models now have this capability. In addition to doing conversation, it can do certain tasks which are like over like at this point it is not fairly complex, but in like newer models which will come in near future, they can accomplish or complete these fairly complex tasks as well. Like so, here in narrow domains like chat alignment, small focused data sets can perform strongly. So idea is like if you want to align your model to a particular domain, so you only need a few set of instructions for the model to train it. Like for example, in the earlier, like in last year, state of the art models use only around 10K instructions to perform best on certain benchmarks. Now, let me So I'll just give you first an idea about like what does instructions look like. So this is how the data for the instruction fine tuning is created. So let's say if you ask what is the capital of India, so that is your query, that is the prompt, and the answer to that prompt is the capital of India is New Delhi. Okay. So now you supply these kind of instruction pairs, that is question answer pairs, or instruct prompt response pairs, whatever you call it. The idea is given this particular query as an input to the LLM, the pre-trained LLM here, we should be able to generate these tokens which corresponds to the answers. Okay. I hope that this makes sense. So now as I mentioned earlier, this is again the way of training is the same as you train a pre-trained LLM. The object function, the loss function is cross entropy, where you try to predict the next token. You try to minimize the generation of the next token, the predicted token, and the ground truth token. That's a cross entropy loss. So now, what are the key differences from the pre-training stage? So we compute loss only on completion token. So the model learns to produce responses, not to predict the user queries. So now in this case, in the instruction fine-tuning stage, we predict the complete response that is supposed to be generated by the LLM. So the predicted response is matched with the ground truth response instead of just giving, providing it the few set of tokens. So the loss function remains the same. So maintaining the same loss function with masking controlling which tokens contribute to the loss. So your initial input, because in the pre-training stage, what happens is we supply the initial token and then expect the model to predict the second token. And then if it didn't predict the second token, we replace the ground truth answer with the second token. And then we provide these two tokens as an input and ask the model to predict the third token. But in here, we are passing the complete input question or input prompt as an input and then asking the model to predict the complete set of answer. Right? Hope this makes sense. This is clear. Yeah, and for the, let's say if this particular question, right? So this particular data example, if let's say the user asks a follow-up query, so the capital of India is New Delhi, then the user asks what is the capital of, let's say, Rajasthan. So now this is going to be, these are not disjoint, these are kind of disjoint queries, but let's say if the initial query is what is the capital of India, the response is the capital of India is New Delhi, and the user asks, what does it is most famous for? Okay, the user asks what does it is. Now it is referring to the New Delhi, right? So what does it is most famous for? So probably this is a multi-turn kind of conversation. So you realize that there is some context which is already present in the previous turn of conversation, which is now should be referred while you are going to predict the answer to the second conversation or the second prompt by the user. So this is kind of a multi-turn thing that we call this a multi-turn conversation. So here we also create such kind of data which have multiple question response pairs, prompt response pairs, and then train the model on these kind of instruction response pairs, multiple instruction response pairs. So now the key difference is that instead of feeding the raw sentences, the model is fed well-structured instruction pairs to limit the learning to produce tokens that form question answer format. So this means that the model needs to be taught to produce full answer to the token, like answer with, let's say if you have answer containing T tokens, so the model should predict the complete answer up to T token. So the idea is like, when does the model know when to stop, right? Because the model doesn't know a priori that it has to generate T tokens. So there is this maximum sequence length flag which helps to constrain the model to stop producing responses, and the loss is clipped at this particular Tth token. So in the ground truth, we have a special end of message token that helps the model to understand, like you have to stop at this particular length of token, and then your loss is only going to be calculated for these tokens, for these many tokens. In addition to this, aggressive fine-tuning may cause the model to lose its pre-trained knowledge, general knowledge. So like pre-training has happened over trillions of tokens. Now, if you do very aggressive, like if you set the learning rate to be very high, then the model is going to learn the knowledge that it learns during the pre-training stage. So the common mitigations to avoid this knowledge forgetting, is like you include dropout, you use smaller learning rates, do early stopping, do not let the model train for a very long time, do a weight decay so your weights are not perturbed in a very high magnitude, and so on. So one of the effective approach is to begin with small instructions and gradually introduce more complex, like multi-turn instructions. Similarly, like first smaller context data sets are introduced, and slowly the data sets with higher context lengths, with increased context length are introduced. So this is kind of a curriculum designing which helps you to make the model learn step by step, like how kids learn. You teach very smaller sentences, or very few words to the kid when it starts to learn, and then later point of time the kids get older and it adapts to even paying attention to a longer set of sentences. So this is like one of the curriculum strategy to make the model learn itself. So this we already seen, like what is the kind of data set that goes during this fine-tuning stage. Now, importantly, this supervised fine-tuning changes all the model parameters. You can also do a LoRa kind of strategy for the supervised fine-tuning, but it is not suggested because if your model has not learned, because we don't do anything much with the pre-trained model, right? So you learn the complete, all the set of parameters are learned during the supervised fine-tuning stage. So we know, like in pre-training, the scale of data set is very large. However, in SFT, the data sets are very small, like a few thousands to few millions. Uh, but these needs to be very highly curated. So that makes them very sensitive to flaws, like even a small fraction of low quality examples can teach wrong behavior. So the recent papers have recipes that emphasize like you need to do rigorous curation and decontamination of the SFT data to build good models. So we do such kind of process, like you do consistency checks, you to avoid like label noise, which comes from human annotators because they tend to produce answers that are wrong, incomplete, or inconsistent. And then there are issues like distribution mismatch, which could arise when SFT data is too narrow. That is, let's say if you're only focused on math problems or short answers, so they cause if your data consists of these many or only few domains, then your model may not be able to answer to the out of domain or your different domain questions and answers. So that's why like you try to mitigate these risks by using filtering techniques like quality checks. You augment the data by balancing domain distribution by sampling more from diverse tasks, prompting uh, higher quality models to generate these data sets and so on. So there are like different ways, but idea is the data quality is very important for this particular stage, more important than the pre-training stage itself. Yeah. So now let's come to, we have seen the pre-training versus SFT. Now let's look at this particular example. Like what does the SFT model output and the aligned model output? We are calling it RLHF, but let's remember that as this as an aligned model output. So the question is, what is a transformer language model? So the SFT model replies like transformer models are type of neural network architecture that have been developed for NLP, natural language understanding tasks such as language. They were originally only used for tasks that require understanding text. So this is like good enough, answer to the question. But let's say if you do additional alignment training of your SFT trained model, how does the answer looks like? So transformer long language model is a neural network architecture designed specifically for NLP tasks based on the transformer model introduced by Vaswani et al. In their 2017 paper, Attention is All You Need. Unlike traditional RNNs or LSTMs, transformer models utilize self-attention mechanism to weigh the importance of different words in a sentence context without requiring sequential data processing. So you see, like there is more information compressed within this particular paragraph than these paragraphs SFT trained model, and this looks more intuitive or more the human or all of us could probably rate this particular answer, the aligned model answer, as higher than this particular answer. So that's the purpose of the alignment stage, to produce answers which are preferred by actual humans. Okay? So that's why I started with this example to motivate you about the difference between the SFT and RLHF trained model. Right? Yeah. Now, once your SFT model is trained with you. Now, how do you create a model that can go into the public? So this is an example of like once you have trained your a model with supervised fine-tuning, once that is done, how do you train with make the model to go into a ChatGPT or a public interface? Right, so you collect demonstration data and train a supervised policy. Like, so here you create data which consist of instruction response pairs, and a labeler, human annotator demonstrates what should be the desired output behavior, and you use that to data to fine tune the pre-trained model. Now, once your supervised fine tuning is done, the step two is to collect the comparison data. So given a prompt and several model outputs are sampled. So for example, for this particular question, explain R into a 6-year-old, there are multiple set of answers that is produced by the SFT model. So these answers are produced with different temperatures, or with different sampling strategies. Like there are greedy decoding, there is a beam search that produces answers. So the model produces different answers to the same question, and then a human annotator rank the outputs from best to worst. It could be a simple rating like from 1 to 5, or it could be more fine-grained rating in the sense like human can annotate like the 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 grammatical correctness of the question, uh, how intuitive this particular answer is. So, like you can do from very broad rating to even a fine-grained rating. So this like differs from model developer to model developer. And once you have this kind of data with you, like in either in the form of ranking or either in the form of rating, then you use this data to train your reward model. So what is this reward model? So essentially, this reward model is a copy of your SFT model, where the last layer is replaced with the probably a regression output layer. So that last layer will produce the the scores for the given input. Right, so we only train for when we train this reward model, only the last layer parameters are learned, where the output is expected to be either in the form of rankings or either in the form of like scores, some real valued scores. So this is a reward model. This is again a separate model, copy of the model, original model, which has been trained on this kind of inputs and outputs. Okay, so this is an input, and this is your these four are your options, and then the objective of the reward model is to score these options. Now, once this reward model is there with you, now how do you train your model to align or change the parameters to align with this kind of preference? Like here you are assigning preference here, right? With score and ranking, we assign preference to a particular answer or not. So the preferred output is particularly D. So how do we train the model to produce this preferred output? Now, once you have, so now you go again with the SFT model, you try to ask a question, and then your there is a PPO. So we'll go into this a bit detail. We can just call it, this is again a PPO model. This is my this SFT model itself. Now this generates your output. Now the generated output is scored by this reward model that has been learned in step 2. And this whatever score, we call it reward because we call it reward model earlier. So this reward is being now used to train the parameters of your original SFT model. So basically, this policy is the gradients in which the model parameters will be learned will be dependent on the reward that is being generated or that is being given by the reward model. Right? So you try to optimize a policy against this reward model using an algorithm, you call it PPO. This is the reinforcement learning algorithm. As I mentioned, this is like you want to generate more aligned output. You want to ensure that the output that is generated by your supervised fine-tuned model is highly scored than the other outputs, or then probably the other outputs that could be generated at different temperature or at different configuration, right? So how do you collect this data? Now, from the start of the ChatGPT, you might have observed that it used to ask like if the answer is correct, you should do a thumbs up or a thumbs down, right? That was a prominent feature earlier. Now it has been the font size or the size of that icon is reduced. But that's how we have trained the ChatGPT model by giving them the feedback by giving upvotes and downvotes. So this is the best way to collect the preference data, and this preference data becomes a USP for these model developer companies like OpenAI, Anthropic, Gemini, and so on. So even though the pre-trained data in the world is limited, in the sense like the public data has these many number of tokens, and you can also scan the proprietary sources, let's say from news media, from private releases, from private books, and so on. Even though all the model developers across different companies could do that, the key difference remains here, where how do you generate the preference data for the model, for the RL policy to be trained and make your model better. So like this is one of the way these model developer companies like OpenAI, Anthropic, and other developer companies tries to give interface to the to the human annotators to give these kind of answers, like if answer A is preferred or answer B is preferred, or both are bad or both are like tied, they are equally bad or equally good. So this is how this interface to the Hamilton annotators are provided. And the other way I already told you about, like they are capturing answers, feedback from us to improve their models. So you might have seen like the capability of the model, not only in terms of how broad coverage of the domains they can do is improved, but also the way they are producing the answers. Now I've seen like in the recent last week, the Perplexity engine is now, if you're trying to learn certain topic, let's say if you ask, tell me how PPO in reinforcement learning works. After certain few conversations, it will give you a prompt. Do you want to test your knowledge? Should I create a quiz for you? So this kind of things. So now, as the time went, that these models have now these edge over the models which will be newly developed by because they have more preference data with them, more information about how user interacts with their models. Right. So yeah. So again, this is good response, bad response, flag, and so on. This is again another example of how these companies collect the data. Now let's come to the actual training process of the alignment model. So SFT model, we have seen like there's not much difference. There's only difference of how do we provide the input and do the token generation. But in the RLHF alignment training, we have this reward model. So as I mentioned, reward is a scalar value indicating the how desirable a particular action or a state is. So this comes from a reinforcement learning literature. So that's why there is an action and there is a state. Okay, so don't be like too baffled by this. So standard way to train a reward model is by using preference measures that measures the probability that the pairwise comparison for two events drawn, let's say, which are drawn from the same distribution I and j. So you just have to give a reward like what is the probability of I being drawn from, let's say you have a box of 10 balls, each having 4 red and 6 green balls. What is the probability of having fetching a red ball from the 10 balls drawn from 10 balls of this distribution? Then this. So this is just a counting measure, particularly not even Bayesian estimate. Now, for in the context of the language model, for two completions, let's say y1 and y2, the complete answers for a given prompt, what is the expected preferredness probability for preferring y1 over y2, right? And yeah, and maximizing the log likelihood of this particular function, one can derive like the loss function the new loss function will become. So that once you do a maximum likelihood estimation, log likelihood of uh, uh, this particular function, you will get this particular uh, you know you will get essentially a sigmoid function which tells you like what is the probability, what should be the loss in terms of the rewards for the chosen answer and the rewards for the rejected answer, right? So as I mentioned, there is a small linear head last layer to the language model that performs classification between two outcomes. So this could be classification, this could be ranking, this could be rating, and so on. And so that's how like a reward model is trained. It's just on this particular simple function, and we just do like this train over this, find out the what should be the loss or reward for the particular set of pairs. So yeah, that is about the reward model. And now coming to the different kind of rewards, as I mentioned, there are different type of rewards that are helpful in aligning the model and improving its capability. So RLHF helps the model excel in general chats and align its safety behavior uh, by leveraging reward models trained from human preferences. There is another reinforcement learning from AI feedback. Uh, it was proposed by Anthropic, uses an LLM together with a written, constitution. So it's a set of policies to scale supervision and generate preference signal. So basically, it generates the scores basically from the AI just comparison, AI models itself to generate these scores. And there is like constitution, which is a kind of a policy which helps the model to rate the or to guide rewards for those particular set of completions by the AI model itself. Then there is another RLVR, which refers to reinforcement learning with verifiable rewards, which helps improving math reasoning and coding tasks by using ground truth answers, unit tests, signals. And there are like other ways to do that. So the idea is that there are like different types of rewards, ways in which you can provide rewards and help the model to improve. So this is again an example of like if the prompt is explain what a VPN to a 20-year-old. So then there is like, as I mentioned, you can give fine-grained rewards like how helpful the answer is, how factually correct the particular answer is. So this helps the model to again build better answers in this. Now let's come to the topic of how does this RLHF training overall works. So there are like hundreds of prompts that are available from the human annotators from on these attributes: how truthful, harmful, quality, how well is the response aligned with the initial prompt, and so on. So these are you have prompt data set, you have your initial SFT model, and then you have your reward model that helps you in which are trained on these sample and reward pairs because you were collected from the annotators, and then these a reward model helps you align the or train the PPO policy or train the PPO or any other kind of DPO to optimization setup to train the model. So we'll come directly to the the policy optimization itself. So in LLM post training, we'll start with the SFT model, which we call it as a policy, which is a policy. So basically, let's say we call it pi, and a frozen reference model, which is also the initial SFT model. So there are two models. One is frozen, and the other is which is for which the parameters need to be learned. So basically, it's a trainable. All parameters are trainable. So for a prompt X and a model output Y, we can define a scalar reward using the reward model. Let's say, this is my R. So R theta Yx is my reward model for the given X. What is the desirability of my output Y? We then optimize a KL regularized objective this particular scale divergence kind of objective with some regularization, which apply policy gradient updates while penalizing divergences from the reference model to prevent drift. I mean, so basically you try to penalize the model if it drifts away from the, from the reward signal, and if it is aligned to the reward signal, you try to generate answer which is more aligned to the reward signal. So essentially, the reward signal can reflect actually the preferences, the outcomes, or even stepwise score. Like we have seen earlier, like there are different ways to assign scores or create these rewards. So the equation above is to maximize the expected reward, this particular reward, while constrained by the regularization using the scale divergence. So in the first term, Rxy is the response, which is a scalar reward computed after the full answer is generated. Pi is my current policy, which is the model that you are trying to train, which is the SFT model. Scale divergence measures the difference between the two model, which is the frozen model, and the one for which the parameters have been updated. So it's an iterative process. The parameters have been updated. There's a new model, Pi. Not essentially the new model. There are new parameters that have been perturbed. The new set of parameters are there with this particular policy Pi model, which this particular term tells us how far your current model has drifted from your initial frozen model. So we do not want the model to drift too far from my initial frozen model, so my initial SFT model, because if it goes too far, then this particular terms helps it to align. So if your model is generating answer which has very poor reward, even in that case, this particular term in the KL averages basically try to do not drift it too far away from this particular model. So this is similar to like a kind of a reference line where you do not stray too far from the original strategies or you face penalties. Okay. So this is like a KL penalty here. And again, this is how this model is trained. So this is the overall way of how this policy optimization works. Now in the PPO training, the actual training, how does it work? So you answer sample K answers per prompt. So here initially you sample K answers per prompt from your frozen model initially, and score each answer with your reward model, which gives you RXY. So X is an input, Y is an output, and now you compute advantages. Like you use the compute advantages A equal basically telling you like how much what is the mean reward across your K samples for that particular prompt, right? So I initially mentioned you need to sample K answers per prompt. So you have to generate these K responses for each prompt. Now, once you do that, you score each answer response using the reward model, and then you compute the advantages using the rewards and the value network. So, and now once you do that, so there are different ways. How do you normalize the advantage? So you take a mean across the K samples for that particular prompt, and there are other ways also to align these, calculate these advantages. And once that is done, you update your actor model with the clipped loss and train the. So your actor model is again the SFT trainable model. You update that with the loss and train the model with MSCT targets. And as I mentioned, you try to control KL to stay near a target by trying to not allow it to stray away too far from the from the frozen model. And once that is done, you update your parameters now to the new state, and your initial policy model becomes the new policy model after this particular training of the batch. Now, as I mentioned, there are like different ways to do it to calculate the advantage. So after PPO, proximal policy optimization, there is also grouped relative policy optimization, which was used in the DeepSeek kind of model. So in this case, you sample again K answers, score them, and give each answer a relative advantage by subtracting a group baseline, right? So you try to push up the log probabilities of tokens above baseline answers. So once you get that mean reward, right? So you try to increase the log probabilities of token which are above this mean reward line, so baseline answers, and push down those log probabilities which are below the baseline while applying a KL anchor. So KL divergence is always there to allow not to prevent the model from straying too away. So yeah, so the GRPO training loop looks like you do not need a separate value network for the critique. So we didn't went into this value and critique too much into for this PPO training. But the idea here is that you do not need a baseline to give the importance of different answers generated for a given prompt. So you use this as a group baseline, which is kind of a mean reward for the all the answers that has been generated by the model for the same prompt. And then there are again different ways to improve preference tuning. There is a rejection sampling. So what happens in this is this was used very popularly in Llama 3 and I think in Gemma as well, this rejection sampling. So these prompts can come from many sources, but they come from the instruction training set, as we know. Because we have in the instruction training set, because we have curated those instruction response pairs, so we use that as our prompts database. So for each prompt, we generate completion, and we can represent this as a matrix, right? So where let's say if you have for a given prompt, you have k completion, so you have k rows with you. Now we pass all of these prompt completion pairs through a reward model to get a matrix of rewards. So we get the reward. And now instead of each reward is computed, through a reward model. And now you only select top n completions. So there are multiple methods to select the top completions, right? So instead of that, you only select the completions which are highly rewarded by your reward model, right? And you reject all the answers which are below a certain threshold. Right? Hope this makes sense. So from the reward matrix, you only define a selection functions that operates on that matrix to only select the answers which are above a certain threshold. So and you reject all the other answers. So this is like rejection sampling, which is more like you would probably try to understand like you do select only a few set of answers with you. And now once that is done with you, okay, we have 3 minutes now. So once that is done, your pre-training has happened. Pre-training we have covered, SFT we have covered, and RLHF also we have covered. Now, how do you evaluate once your post-trained model is available with you, right? So there are different ways. One is using ground truth-based evaluation, like you look at the benchmarks where the input and output is given to you. And then the other way is using LLM as a judge to evaluate your model outputs. So we'll start with like ground truth based. So for tasks such as math, problem solving, coding challenges, or multiple choice reasoning, the correctness can be automatically checked by looking at the final answer, right? It's quite simple and straightforward. Like, so human evaluation, like there are various ways to, get an answer, like you annotate as, I think this is list. Yeah. So now there are different ways to do this evaluation, like you do point-wise evaluation, like in terms of, how helpful this particular score is. But I think this is again from the point of view of reward model. I'll just go back to this slide. So now, yeah. So now you can do this ground truth based evaluation by looking at various benchmarks. Like we have several benchmarks like MMLU for evaluating general knowledge understanding or higher school understanding of the LLMs. And there are like picture-based question answering. So there are different multimodal and textual-based benchmarks which are available. Now there are like for the automatic evaluation in terms of using a bigger LLM. So let's say if you developed LLM and now you use ChatGPT or Claude as your judge, LLM judge, which will score the how good is your model in let's say in these attributes or the overall score. So you use that model, the bigger model, maybe proprietary or let's say a bigger, very big DeepSeek 671 billion parameter model to evaluate your developed model. So the answers that will be generated from your model will be given to this bigger model to evaluate like how good is your particular model, is this particular response. So then you use this as an evaluation way to way of evaluation, right? And these evaluations work well for like open-ended tasks like summarization, reasoning, summarization, dialogue, creative writing, and so on, where multiple valid answers can exist, but we can evaluate on tasks such as helpfulness, correctness, clarity, and so on. Right. So this was again, yeah. So in addition to like what we've seen of preference data creation, this is also used to you know using automatic evaluation by using LLM as a judge to score on these attributes. I think this is it from my side. I think we can take questions at this point of time. Yeah. So if you have any questions, please feel free to ask. I've already posted this presentation on the GitHub. We'll probably write this GitHub repository. All the sessions have been like posted there. I'll just mention the repository again here. So you can check that.
So thank you for joining. Thank you, Ayush. We can close it.